Welcome friends to this session of our discussion. In the previous discussion we have discussed the continuous time system, LQR problem, LQT problem. So, today we will see whether the variational approach can be applied to the discrete time system. I hope everybody will understand the difference between the continuous and the discrete system. In discrete system, we will define a signal at a discrete instant of the time. So, here we will consider the system in the discrete form as well as my performance index also in the discrete form. So, here as we have defined the continuous time functional, similarly we can define a discrete functional, which is nothing but the summation of a functional v, where v is a function of xk, xk plus 1 and k. So, what actually we are considering, if t is my scale and if I will say this is v, suppose any form of the function I will consider and I will have the sampling instant, sampling period as t. So, I can say this is my k0, this is my k1t. So, if I will have the constant sampling, I can define the value of the v. So, let us say this is my some point k. So, I can define this as my Vk, and more general case if we will take, we will write this as V at the instant kt, and this point I can write as V k plus 1 t. So, in normal representation we represent this as Vk and this simply as V k plus 1. So, what we are considering here? We are considering a constant sampling period. So, t is constant throughout all the sampling, k represent the instant where we are having the sampling. So, k varies, we can say from 0 to let us say kf minus 1. So, in this way we can define our any discrete functional, and as we know what is a functional? Functional is nothing but a function of functions. So, what we are trying to do? We are considering a functional j as summation of v xk, xk plus 1 k. More general, this is v x of kt, x of k plus 1 t and kt. So, in normal representation we are dropping out the t and simply representing the function as v of xk, x of k plus 1 and k. So, my this functional is a nothing but summation of the different scalars when my k is varying from k0 to kf minus 1. So, we consider that, so v is we can say a function of another function xk. So, if v is a function of xk and xk let we define this as my xk, and particularly let us say this is the optimal value. So, we are considering let this xk is the optimal value of the x, and we are considering a variation as xk, which is nothing but x star of k plus delta x of k. What is the k? So, let this instant is k 0. So, this is defined as x of k 0, which is normally defined, and here we have considered t is constant. Let us say this is k 1, k 2, k, and my terminal time is up to kf we are considering. Each instant, so my x is defined at the instant of k 0, x of k 1, this is my, if I am defining as my optimal value, x star of k 2, a journal point x star of k, and each point I will have delta x of k. Like at this point this is delta x k 1, similarly I will have here, and let us say this is delta x of k, where k is varying k 0 to kf minus 1. This particular case is shown as my 2 fixed endpoint problem, but normally we are given with the initial condition and the terminal condition depends what actually is appearing, which we will discuss in the later part, but this particular case is shown for a fixed endpoint problem. So, this means what we are saying, we are considering a optimal x and seeing the variation at this optimal point. So, we are saying let xk plus take the variation delta xk and delta xk plus 1 from their optimal values of x star k, x star of k plus 1. So, this means if let us say at kth instant my value is x star of k, next instant to this will be k plus 1. So, this value will be x star of k plus 1. At this instant, this is the variation at this, sorry, this is my delta x of k plus 1. So, these we are assuming at this instant, but these variations are available. So, in journal my xk is defined as x star of k plus delta xk, xk plus 1 as x star of k plus 1 delta xk. So, this means if this is my xt, let this is the continuous trajectory xt. At different instant I know the value at k0, k1, k2, k plus 1, kf, and at each instant I am defining my xk as x star of k plus this delta x k, and similarly, so this is x k is defined as this point, and at this point we are defining as x k plus 1 as x star k plus 1 plus delta x of k plus 1. So, this is at the instant k plus 1 and this is at the instant of k. So, I simply define x k as x star k plus 1 delta x k plus 1 as x star k plus 1 delta x k plus 1. So, with this x k I will have the optimal value of the j as j star given as v of x star of k, x star of k plus 1 k, and at the variation point x star of k plus 1 delta x k plus 1. So, at optimal point which is at x star of k, my j is v x star of k plus 1 k, and at the variation point my performance index is j defined as v x star of k plus 1 delta x k, x star of k plus 1 delta x k plus 1 x k. What is my objective? I am trying to find out the extremal value of the j, and to determine the extremal value of the j, my j is defined at the optimal point and some variation point. As we know, we can define the increment of a functional as j minus j star. In this j minus j star, we can determine the first and the second variation. By the fundamental theorem of calculus of variation, my first variation must be 0 and second variation should be less than 0 for maxima and greater than 0 for minima. So, for the given value of the j and j star, we find out the first increment, and increment is defined as delta j, this is the j minus j star. So, what I can write for delta j? What is my j? My j is sigma of v x star of k delta x k k0 to kf minus 1 we are finding, and this is v delta x k x star of k plus 1 delta x of k plus 1 k. So, we can say this is my j minus j star is nothing but v x star of k k plus 1 k, this is also sigma. So, this v minus v at x star, and this we can expand using the Taylor series. Which is nothing but k0 to kf minus 1. So, the first term I am expanding using Taylor series. If I will expand this, I will get v, my first term will be v x star k, k plus 1 k minus del v, I am writing simply like this, where v is a function of, okay, write it complete, x star of k, x star of k plus 1 k delta into del x of k. Sorry, this is plus v plus del v by del x k, del v by, so I am simply writing this as dot, you can understand this, delta x of k plus 1 delta x of k plus 1 plus, now second order terms, higher order terms, minus v x star of k, x star of k plus 1 k. So, this term remain as such, and this term we are expanding using the Taylor series. So, naturally these two will cancelled out. If I will neglect the higher order term, I can write my first variation as del v by del x star k delta x k del v by del x star k plus 1 delta x of k plus 1. This means I am representing my first variation as del v by del x star delta x k del v by del x star k plus 1 delta x of k plus 1. So, in the first variation I will have the two terms, one in the delta x k, other is the delta x k plus 1. Like in a continuous time case, we have the x dot term in place of the x k plus 1, and we are converting this x dot in terms of the delta x. So, similarly here we will see, can we convert this second term in terms of the delta x of k. So, what actually we have? We have the first variation as del v by del x delta x del v by del x k plus 1 delta k plus 1. So, just consider the second term delta j as, sorry, we consider the second term k 0 to k f minus 1, we consider del v x star of k, x star of k plus 1 delta x of k plus 1 delta x k plus 1. So, we are considering the second terms of the first variation as del v x star k plus 1 x k by del x of k plus 1 delta x of k plus 1. We expand this with taking k as k 0, k 1, k 2, k f minus 1. So, my first term will be del v k 0 x star k 0 plus 1 k 0 differentiated with respect to x of k 0 plus 1 delta x of k 0 plus 1. So, I write second term will be del v x star k 0 plus 1. My first term is the k 0, second term will be k 1 x star k 1 plus 1 k 1 by del x of k 1 plus 1 delta x of k 1 plus 1. So, this will be my second term. So, similarly, I can have the third, fourth up to second last term. If I will write, this will be del v kf minus 2 x star kf minus 2 plus 1 kf minus 2 by del v del x kf minus 2 plus 1 delta x of kf minus 2 plus 1. So, this is my second last term, and what is the last term with kf minus 1? That is del v kf minus 1 x star kf minus 1 plus 1 kf minus 1 del x of kf minus 1 plus 1 delta x of kf minus 1 plus 1. So, this gives me nothing but the expansion of this summation, the second term of the first variation which we have considered, by k replacing by the k 0, then k 1, second last term kf minus 2, last term kf minus 1. So, in this, if I will add the two extra terms, one term I will add and subtract, which is del v x star k 0 minus 1. As per this, next will be x star k 0 minus 1 del x k 0, because we have to take the k 0 minus 1. So, this is k 0 delta x of k 0, and the same term I will subtract from this del v x star k 0 minus 1 x star k 0 minus 1 delta x of k 0 delta x of k 0. So, if I will add and subtract this term, so I am not going to change my relation. So, now what we are doing, I am including this first term as my first term of this expression, and these two terms I am combining together. So, if I will say I am not going to change the number of terms here from k 0 to k f minus 1. So, this whole expression, so what I have done, I have included this term as the first term of this expression. So, this means I am writing the second term as sigma k 0 to k f minus 1. So, what I will have? I have only up to this term. This is my first term. So, this V I am changing by x star of this, I am writing as x star k minus 1 x star of k by del x of k. My first term is this, second, third, and this is the last term for this expression. So, if I will take the k 0, my first term will be del v x star of k 0 minus 1 x star of k 0 minus 1 delta x of k 0 delta x of k. So, this will be my first term, this will be my second term, this will be my third term, and this will be my last term. And I am writing this last term as del v x of k sorry and this is k equal to k 0 and k equal to k f. So, these two combined term can be written as del v by del x of k minus 1 x of k k so del v by del x of k at the instant k 0 to k f minus 1. So, now the second term can be replaced as del v by del x of k delta x of k del v by del x of k delta x of k at k equal to 0 k equal to k f. So, these last two term giving me this term, and these another terms are giving me summation of this term. So, this del v by del x k we are writing as summation of del v x of k minus 1 x star of k x k minus 1 by delta x of k delta x k. So, this first expression I am getting with these term except the last except these two terms, and these two terms I am combining together to get my second terms of the first variation as sigma of del v x star of k minus 1 x star of k minus 1 by delta x k plus this is my condition, this term is out of the summation, but evaluated at the value k equal to k 0 and k equal to k f. So, what actually we have done for this second term, we have converted this delta x k plus 1 in terms of the delta x k. So, this term we are expanding with the summation of this. So, this whole can be clubbed in the summation with the first term as given at this point. So, this will have the delta x k, this will have the delta x k, and these two term I can write as my boundary condition given as del v x star k minus 1 x star k minus 1 del x star k delta x k from k 0 to k f. So, the overall I can write by clubbing these two, my first variation will be summation of del v by del x k, del v by del x k with delta x k, but this v is a function of x star k plus 1 k, and this is the function of x star of k minus 1 x star of k minus 1. So, like we got in our continuous time system del v by del x d by dt. So, because here we have the one step before, as I am finding, like in the first term we have the del v at x star of k, this is a one step before x star of k minus 1. So, means analogous to, we can consider it like we are taking the differentiation d by dt of del v by del x dot we have taken. So, here we have taken del v by del x k. So, these two term now can be clubbed with delta x k, and this is my last term, last two terms which we have taken here. These last two term we have clubbed together just to get the value of k equal to 0 to k equal to k f minus 1. These 2 point I have to evaluate. So, this gives me nothing but my boundary condition, and this is nothing but the summation. So, this is my first variation, this delta j, by clubbing these term, this first variation must be equal to 0. This is my fundamental theorem. So, if I am to find out the extrema of a functional, its first variation will vanishes at the optimal point. So, I can equate it to 0. As my delta x k is arbitrary, so delta x k can take any value. So, this whole equation to be 0, the coefficient of the delta x k must independently be 0, and this boundary condition second term will also be equal to 0. So, we can say the arbitrary variation delta x k, coefficient of the delta x k be 0, and this is called my discrete time version of the EL equation. For the boundary condition, my second term must be equal to 0. Now, depending upon my boundary condition, the different boundary condition can arise. If I have the fixed endpoint condition, then k equal to k 0 and k equal to k f, my both the points are fixed. So, in this particular case, my delta x k at k equal to k 0 and k equal to k f will be 0. So, this equation will not arise in the system. In normal case, we will have, we are basically given with the delta x k 0 is fixed. So, delta x of k 0 will be 0, but normally delta k f is free. If k f is free, then delta k f will not be 0. So, I can say the my boundary condition with delta x k equal to 0. So, that part will be 0, but my boundary condition will be del v x star k minus 1 x star of k minus 1 by delta x k at k equal to k f point, then this condition will be 0. So, similar like we have in a continuous time system, we have solved the extremization of the functional for continuous time case. So, we will land with a EL equation and the boundary condition. Similarly, for the discrete time case, we have the analogous EL equation in the discrete form as del V, which is a function of xk plus 1 k differentiated with respect to delta xk plus del V, which is a function of x star k minus 1 x star k minus 1 differentiated with respect to delta xk. The summation of this will be equal to 0 is my EL equation, and at if initial condition is 0 then and final initial condition is given and the final state xkf is free, then this will be my boundary condition. So, I end this session here. Thank you very much.